Hey guys, how are you? Um, See, I realized teaching past 16, 20 hours that your attention spans are very low. Okay. Um, so what I thought is in the class, you may lose me very quickly and may not follow some of the concepts. I'm giving a very detailed text which should be sufficient if you read it. But I also felt some of you are not probably, the people they have different learning styles. Some of you probably learn better through listening. So while I will not try to do all 5 sessions, that is 10 hours, I will probably do these videos for the most important topics. Okay. I at least for this particular exam that you have next week, as I said, calculus takes a big thing. Simulated annealing is an important thing, and the dynamic programming. I thought I could just do those 3 lectures to begin with. Okay, so that is the objective of this interaction. Okay, now let's start with calculus, finding maxima minima. That's what we are doing. In the simpler case, which you are familiar with, let me take the example that I have used in class itself and the notebook, x square minus 2x plus 1. I want to find the maxima or minima. Because it's a quadratic, you can eyeball it, you can see there is a minima here. Global maxima is infinity, it goes to infinity. But let's calculus only finds the local minima, local maxima. There's no local maxima, so I think most likely calculus should find this. How do we do that? First, we will do the differentiation, and this is 2x minus 2. Okay, so this to find exactly where the minima happens, we have to make this equal to 0. So x is equal to 1. So this thing takes a minima or a maxima at x is equal to 1. Then whether to figure out whether it takes a minima or maxima, we will do one more time, we'll differentiate this one. That will become 2. If this is a positive, at this point, it's a minima. If that was a negative, it would have become a maxima. Okay, let me write it nicely. Okay, minima, maxima. That is the nicest that I can write. Anyway, so this one you're already familiar with. Okay, um, but the the where things got really tough for you. Let me look at your notebook. Where things got really tough for you. Well, in the class, I actually did one more example of a one-dimensional thing with a slightly more complex equation, x cubed by 3. Um, f of x is equal to x cubed by 3 minus 3x squared by 2 plus 2x plus 4. But the method remains the same. First, I will compute that first differential. This x cubed by 3 will become 3x squared by 3, which is x squared, minus 2 times 6x by 2 minus 3x plus 2. Now I have to equate it to 0. And one way to do it from our past birth, we know that. And then we take x out and we do this thing. So x is equal to 2 or 1. That's what we understand. X is equal to 2 or 1. Now, uh, now we do f prime of this thing, this guy. One more time, f double prime. One more time, because I know maxima or minima will happen here. But is it a maxima or minima? Differentiate again. 2x minus 3. If I substitute 2 times 2 minus 3, which is equal to 1, greater than 0. So this point is my minima. We agreed. If it's positive, let's call it it's a minima. 2 times 1 minus 3 minus 1 is less than 0. So this guy is maxima. So that's how you do it, right? And if you look at the graph, again, some local maxima, local minima are identified. Good. Now, this part is clear to you. But the real challenge, and obviously where you will be tested, is when we do it in higher dimensions. Now, the point is higher dimensions. Here you will see two kinds of complexities in higher dimensions. The first complexity, wait a minute. The first complexity is, where is my browser? Uh, is so let's go to images. So take this point. If I look in this direction, this is a minima of this curve. If I look at this direction, if I look in this direction, this curve, this is a maxima. So that green guy there is a saddle, is minima in one direction and maxima in the other direction. So that is the kind of um, complexity that you never had in uh, one dimension that you will get. So in one dimensions, you have maxima or minima. Here you have maxima, minima, or saddle. Now there is one more complexity that we have to look at, but we will see that when we get to it. Let's take a curve with two dimensions. Fx is equal to x square minus y square. Now let's do f prime x. Sorry, this is not fx, this is fxy. Okay, so f prime xy. Now the way we do it is we will first find the critical point in x direction where y is kept constant. That is represented as dou f by dou x, which means I am now only variable is x. I'm moving, for me, y is a constant. Dou f by dou x is equal to 2x. Similarly, I'll keep y constant. Dou f by, sorry, y variable x constant, dou f by dou y is equal to minus 2y. So those are our critical points. And when will they be equal to 0? Independently, I have to make them equal to 0. 2x is equal to 0 and hence x is equal to 0, y is equal to 0. So the critical points are at x is equal to 0, y is equal to 0. Now the second complexity comes. How do I know whether they are maxima or minima? I have to do double differentiation. But do I double differentiate this or this with respect to x or y? To get solve that, you computed two things already. Dou f by dou x, this is 2x. Dou f by dou y, this is 2y. Now let's double differentiate with both dou by dou x and dou by dou y, both of them. So dou by dou x of dou f by dou x, they write it as dou square f by dou x square. So I differentiate this 2x with x, which is equal to 2. Dou by dou f by dou by dou x of dou f by dou y. This is dou square f by dou x dou y. Again, this is 0 because for me, this 2y, I'm differentiating only with respect to x. Y is a constant in that differentiation. Okay. This matrix always will be symmetric. So you don't have to really compute it, but let's compute it for practice sake. So dou by dou y of dou f by dou x, dou square f by dou y dou x. as expected, y, and here only 0, 0. Dou square f by dou y square is equal to, hey, this is minus 2y, minus 2. So my double differentiation is now a matrix 2, 0, 0, minus 2. So if I have two variables, I'll get a 2 by 2 matrix. If I have three variables, I'll get a 3 by 3 matrix, but it's nevertheless a matrix. How do I know whether it's a maxima or a minima? Here we lucked out. We got a diagonal form. If you get a diagonal form, it's easy. Just observe the diagonal elements. If both are positive, it's a minima. If both are negative, it's a maxima. If one is positive, one is negative, it's a saddle. If one of them is equal to 0, we can't conclude. This information is not sufficient to tell whether it's a maxima or a minima. By the way, this is the condition even in one dimension. If your d square y by dx square is 0, it has to be either positive or negative for you to make a conclusion. If it's 0, you cannot conclude. Okay, so that is the way. But if let's say you got an ugly matrix, like 1 minus 8, 2.5, 3.6. How do I know this is because actually I will not get, sorry, I made a mistake. If I got 1 minus 8 minus 8, 3.6, because it's always be a symmetric matrix. How do I know whether it's positive or negative? I can't. So I put it through a process called diagonalization, okay, where this matrix is converted into a diagonal matrix. And then I observe the diagonal elements. These two will be zeros and I observe. These matrices can all be diagonalized. Number one, they are square. Number two, they will be non-linearly dependent. Don't worry about it. But whenever you do a Hessian, by the way, this one, this is called Hessian. Hessian. Sorry. Let me try to write it nicely. Hessian. And this one, doing dou f by dou x, dou f by dou y, that is called gradient. So your slope and double differential get more jazzy names, gradient and Hessian. Okay, so that's how do you diagonalize? I'll not teach you that. You just go to the chat GPT prompt, give me a code to find eigenvalues or diagonalize a matrix. Okay, when you diagonalize, the non-zero elements of this matrix are called eigenvalues. So you can go to chat GPT prompt. I have a 2 by 2 matrix or 3 by 3 matrix. Please give me the code to find eigenvalues. It will give you the code, copy it somewhere, and then I upload the matrix. This is a someone was asking me in the class about the intuition behind eigenvalues. The way you can understand eigenvalues is take a coordinate system, x and y axis, x1, x2, let's say. A point here will have x1, y1 coordinate, another point here, x2, y2. Now let's take a matrix representation. Let's say there is a matrix, a 2 by 2 matrix, and I multiplied it with x1, y1, which is a 2 by 1 matrix. When I multiply a 2 by 2 with a 2 by 1, I will get another 2 by 1. Let's say I got x2, y2. Okay, whatever, these values. And let's say those 2 points are this. One way to understand this is a transformation matrix that transformed this point to this point. Now, in this basis, to move from here to here, I have to have this transformation matrix. But let's say I rotated the transformation matrix such that uh, exactly they stay perpendicular. So this thing is perpendicular to the new y-axis. Okay, actually, let's move it the other direction. So this is the new y-axis. This is the new x-axis. Now, look it in this angle. This coordinate here will be whatever is the new coordinate A, B, let's say, in this new system, this point. And this will be, A will be as a 0. This will be minus A, B. So this point in this new coordinate system just got transformed. The transformation matrix is 1, 0, 0, minus 1. Am I right? If I multiply with AB, 1 times A, 0 times B, 0 times A, 0, minus A minus B, it's becoming. So minus 1, 0, 0, 1. So that is the transformation matrix. So AB will become minus 1 times A minus A and B, right? So whatever this ugly matrix was, exactly the same transformation. You see, I didn't change the transformation at all. This point went from here to here. But by changing the axis, the matrix became very, very simple. This is exactly equal to this matrix. It is just that my convention previously, it was a different system. Now it's a different system. Now, eigenvectors are those bases where a complex matrix becomes a simple matrix. Eigenvalues are those simple values that it takes. So diagonalization essentially is finding for a given transformation matrix a new basis where it takes a diagonal form. But then the diagonal form is exactly equal to the original form, right? So whenever you see things like this, just diagonalize it, find its equivalent diagonal form, and observe the matrices and diagonal elements, and decide whether you are doing, is it a maxima or a minima or a saddle, or you cannot make a um, conclusion. Let me continue with one more problem where you can sort of, in the text I did x square minus y square, x square plus y square. They are quite easy, right? It's exactly the same thing, x square plus y square, where it turns out that both, the elements of Hessian are positive, and hence there is a minima. So let's take a slightly more complex problem to solve this. Hmm? To practice. So the problem that I took in the class is a three-dimensional matrix f of x, y, z, x square plus 2yz minus 3xy. This z is my US education result of that. They call it z, xyz, 4x square. Right. How do I do? I have to do gradient now has dou f by dou x, dou f by dou y, dou f by dou z. Dou f by dou x is 2x, this will be 0, minus 3y plus 8x. Oh, did I say 2x square plus 4x square? I should have just said 4z square, sorry, 4z square. So this is 0, 2x minus 3y. And dou f by dou y, this will become 0, 2z minus 3x, right? And there's nothing here. Dou f by dou z, this is 0, 2y, 0 plus 8z, right? So this is our gradient. Now I need to solve it. And the solution essentially, again, 2x minus 3y is equal to 0, 2z. Let's do it. Sorry. is equal to 0. 2z minus 3x is equal to 0. 2y plus 8z is equal to 0. This is three equations and three unknowns. So it's a straightforward mathematical thing. I just have to substitute. Let's say I will write x is equal to 3 by 2y. And I substitute. I will not go into that solution. I'm sure you guys figure out how to do it. But it turns out that this is solved at 0, 0, 0. Okay, again, like last time, we got a clean critical point, which happens at 0, 0, 0. So you just have to solve it. Great. Now, is it a minima or a maxima at this point? Okay. One way you can do is to um, um, plot the curve and see, but let's use mathematical, our Hessian. Again, we already computed dou f by dou x, which is 2x minus 3y. Dou f by dou y, which is 2z minus 3x, 3x. Dou f by dou z, which is 2y plus 8z. And again, until you get comfortable, just do dou by dou x I have to do for all three, dou by dou y I have to do for all three, dou by dou z I have to do for all three. So this dou by dou x of this dou square f by dou x square, this is 2, the dou square f by dou x dou y, 2z minus 3x minus 3, this becomes 0. So symmetric, this becomes 0, this becomes minus 3. Dou square f by dou y square, this is 0. Dou f, this is 2, then this becomes 2. This goes at 8. So my matrix now is 2 minus 3 0 minus 3 0 2 0 2 8. Obviously, it's not diagonal. There are off diagonal elements. Unfortunately, this time I have to write Python code. And when I do write Python code, ask it to and compute the eigenvalues, the Python code gave me 2.42. ChatGPT did this wonderful job, 3.86, 8.56. And this is negative. These two are positives, and hence it's a saddle. Okay, great. I will end the discussion here. The good news, obviously, as you can see, is unlike in the class, here you can shut me up whenever you want and focus only on, um, uh, you know, uh, what you can listen to at any given point of time. Let me stop the recording.